The Diary of Dr. X, Episode 18, The Laws of Natural Equilibrium, the Importance of Optimization in Complex Organic Systems. Found a couple bottles of Jagermeister in the dumpster just about 3 days ago. One of the most fundamental characteristics of all complex organic systems, be they the human body, human culture, an ecosystem, or the biosphere itself, is that they function in terms of equilibria and optimization. The centrality of optimization in the successful functioning of all organic systems is the key to understanding a variety of ecological problems, including global warming and acid rain. As Gregory Bateson, one of the most brilliant theorists of the last century, pointed out, it is also the key to understanding the difference between the dominant economic logic of our time and the inherent logic of all other living systems. In his writings, Bateson critiqued the dominant economic or commercial logic of Western society with his contrast between the ethics of optima and the ethics of maxima. As he suggested, the two represent totally different ethical systems. They are ethical systems in the broad sense that they contain values of some sort. Bateson's contrast between optima and maxima was intended to suggest that if we wish to adapt to the type of complex organic systems of which our society is a part, we can only successfully do so based upon an adequate understanding of the nature of those systems and of their own patterns of operation. That's what adaptation is all about. Ecology's central goal. The general patterns of interrelationship in society must successfully mesh with the patterns of larger systems by which they are encompassed if we are to achieve a sustainable society. In contrasting the dominant economic ethic of maximization with the logic of other living systems, Bateson's purpose was to illustrate the manner in which both economic logic and the actions based upon it were inherently maladaptive, anti-ecological in other words. He began by suggesting that, and I quote, "there are no monotone values in biology." By this, he meant the following, and I quote rather extensively. A monotone value is one that either only increases or only decreases. Desired substances, things, patterns of or sequences that are in some sense good for the organism, items of diet, conditions of life, temperature, entertainment, sex, and so forth, are never such that more of the something is always better than less of the something. Rather, for all objects and experiences, there is a quantity that has an optimum value. Above that quantity, the variable becomes toxic. To fall below that value is to be deprived, end quote. Thus, in successful or sustainable organic systems, values are never maximized. Rather, they are optimized. For example, I'm sure most of you probably know at least one insulin-dependent diabetic. Well, as diabetics and those who love them know all too well, blood sugar has an optimum range in the human body. Both too much and too little are damaging to human health. High blood sugar can lead to blindness over time. Low blood sugar can cause a person to lapse into a diabetic coma, which damages the liver and may even cause death. Hence, blood sugar must be maintained within its optimum range to prevent these negative effects. Where food or sugar are used to increase blood sugar, insulin is used to decrease it. In a constant balancing act, basically, which attempts to avoid the damage caused by either of the extremes. A very good example of the importance of optimization in living systems. Similarly, too much food leads to obesity, while too little leads to malnutrition, both of which are unhealthy. Too much or too little water lead to drowning or dehydration, both of which can cause our deaths. Everything that is of value in the human organism or any other living system has an optimum range or amount. Yet Bateson Bateson argued that what applies at the level of the organism also applies to organic systems at larger scales, both cultural and ecological. Plants require nutrients in order to grow, for example, with nitrogen being one of the principal ones, but there is an optimum amount of nitrogen that plants require. If there are too few nutrients, not only plants, but the entire ecosystem that relies upon them for food and oxygen also suffers, but too many nutrients also lead to ecological problems. Artificially maximizing the amount of nutrients available to crops by applying nitrogen fertilizer to fields, for example, leads to a variety of negative ecological effects. These include eutrophication events, or the depletion of oxygen in lakes, leading to fish kills, algal blooms, related to the above, red tides, and methemoglobinemia, or blue baby syndrome, which kills human infants from nutrient pollution. Thus, maximizing agricultural production by maximizing available nutrients leads to a negative ecological consequence because it pushes nutrient levels beyond their optimum range. In fact, dead zones depleted of oxygen now appear in the Gulf of Mexico, in the ocean, on an annual basis, right around the mouth of the Mississippi, due to the runoff of excess nitrogen fertilizers down the Mississippi River each spring. Acid rain is the same, another ecological problem. Acid rain results from changes in atmospheric chemistry from burning fossil fuels, especially coal, the dirtiest of them all. Combustion of coal in particular releases sulfur dioxides, or SO2, while all combustion releases nitrogen oxides. These both react in the atmosphere to form various types of acids, which fall to the earth in precipitation, artificially raising the acidity of bodies of water beyond their optimum levels on the pH scale between acid and base. Once again, maximization of acidity has negative ecological consequences in that it leads to fish kills in lakes that reach acidities beyond the tolerance of their native species. But water that was too base would be equally lethal. Global warming is again the same, in that the atmosphere also has an optimum amount of both oxygen and carbon dioxide. If there were too little oxygen in the atmosphere, all animal life would die. While if there were too much, fires could never be extinguished. Similarly, if there is too much carbon dioxide in the atmosphere, as there is at present, it leads to global warming and all of its unpredictable effects. Levels of CO2 are being maximized or pushed beyond their natural levels. We are, in fact, releasing CO2 much faster than the biosphere can naturally process it. Hundreds of millions of tons annually. Add to that the fact of deforestation on a global scale, which both adds further carbon to the atmosphere and reduces the biosphere's capacity to process it at the same time, and it's easy to understand why carbon is building up in the atmosphere. Forests, you see, are carbon sinks. Since plants absorb carbon from the atmosphere, storing it in their cells, while giving off oxygen. What receives rather less publicity, however, is the fact that if there were too little carbon dioxide and other greenhouse gases in the atmosphere, it would also be a bad thing. The global average temperature would rapidly drop, sharply below the conditions necessary to maintain contemporary life. So once again, this emphasizes the central importance of optimization and equilibrium in all organic systems. Both oxygen and carbon dioxide have an optimum range within the biosphere, with this optimum being maintained under normal circumstances through the operation of the carbon cycle. Where animals breathe in oxygen and exhale carbon dioxide, plants take in carbon dioxide and give off oxygen. Nice of them, isn't it? This is a pattern of a complementarity, which leads to an oscillation about the optimum range for both gases under normal conditions. This sort of oscillation in organic systems is also typical at the ecosystem level. The classic example from population dynamics is that of the fluctuation in population of predator and prey. In general, increases in prey species leads to an eventual increase in predators over time, because they have more to eat and reproduce more quickly. The increase in predators leads to a consequent decrease in prey and eventually in predators as well, as they run out of food and reproduce more slowly. Once again, this produces a pattern of oscillation for both populations around an optimum value. In this case, an optimum population for each species. What Bateson suggests with his contrast between the ethics of optima and maxima, therefore, is that organic systems are deviation-inhibiting systems, which operate in terms of negative feedbacks. The classic mechanical example of a negative feedback system is the relationship between a thermostat and a furnace, where the user is able to set the optimum value, or the desired temperature. Consequently, when the temperature of the room exceeds this optimum value, the furnace will be shut off, allowing the temperature of the room to drop. When the temperature falls below the optimum value, however, the furnace is turned back on. This leads to an oscillation in temperature around the optimum value, which mirrors the patterns of relationship that characterize successful organic systems. The ethics of maxima that characterizes the logic behind capitalist economics, however, is quite different. It is consistent not with negative feedback systems, such as are typical of other living systems, but rather with positive feedback systems. Positive feedback systems are referred to as deviation amplifying systems. In other words, positive feedback systems tend to move consistently in the direction of one of the extremes. An intensification leads to further intensification. A decrease leads to a further decrease in some variable. The classic mechanical example of positive feedback is the breakdown in the intended or optimum relationship between a microphone, amplifier, and speaker system. And I used to work in the music business, so I know something about this personally. For if the sound coming out of the speakers feeds back into the microphone, it creates a vicious circle through which the signal is continually amplified each time it comes back around the cycle. This leads to the familiar high-pitched squeal of feedback, with which we are all familiar in popular language. It also leads to the eventual collapse of the system and can even blow up your amplifiers. Thus, where negative feedback systems tend to maintain themselves by oscillating about an optimum value, positive feedback systems tend to escalate out of control. One pattern is sustainable, the one we want, while the other, economic growth, is self-destructive and eliminative. A thermostat furnace system that went into positive feedback mode, for example, would be unable to compensate for increases in temperature by shutting the furnace off. Instead, if the room became hotter, the message would be that the room needed to be made even hotter still. And eventually, and here's your lesson, the house would burn down as a consequence. What this implies is that economic logic promotes a positive feedback system of endless growth, which is not only inherently unstable and destructive, but also moves according to a pattern that is totally at odds with the successful functioning of organic systems. That is, it is completely maladaptive. Consequently, the ecological destructiveness of this economic logic and the technologies it creates are hardly surprising. Bateson's central message is precisely this: consistently maximizing any variable in a living system, including profit, eventually leads to the death of the larger system of which it is a part. What we need, therefore, is not maximization of profits, but optimization of production. We need optimum production for an optimum human population. We need technologies that do not interfere with natural chemical equilibria in the biosphere. Finally, we need levels of population and production that are sustainable over the long term. And any systems that is likely to meet these criteria is going to operate in terms of optimization and negative feedbacks. That is, in terms of equilibria. And that sounds a lot like a zero-growth economy to me, or perhaps more appropriately, an economy of optimal production.